We have passed almost halfway of the total seminar time. I have a huge collection of slides to show you, but I will hurry as much as I can. So making all these calculations in the limit equilibrium world leads us to a determination of a factor of safety, no matter what you're dealing with. In a typical slope stability problem, just as a reminder, you see that we normalize resisting forces with the driving forces, and if they are in the state of limit equilibrium, the critical state, then they are equal. If factor of safety is less than 1, we call it as unstable. If it's greater than 1, it is stable. But our initial comment is that, is this so simple? There are many uncertainties associated with characterizing the rock mass or soil strength, parameters, structural loads, geological conditions, hydrogeological conditions, and all of them carry their inherent uncertainties within the nature. Speaking of support elements within a soil structure, for instance, there's also discussion whether we should include them as supportive forces in the resisting forces size denominator, or subtract them from the driving forces in the aspect that they are mobilized as active or passive. So the discussion goes on, and most of them are relatively answered, but they're not very new. We can imagine that subjects, but just out of curiosity, we wanted to share what's happening and how to see the big picture and make decisions. So our tolerable factors of safety at every industry, every problem we're facing with are different and should be different. They vary from practice to practice. They vary from region to region all over the world, as well as the specific project that you're working on. And this all concludes to a fact that the amount of risk that you should be tolerating is actually a definition, a statement of the safety factor that should be you should be using. For soil earthworks, for instance, they begin from 1.3 to 1.5. Of course, under the effect of static loading, for retaining structures, stability considerations are factors of safety increases once structural loads are imposed into the systems. Once we are in the world of dam engineering, they can lower down to 1.2 and increase up to 1.5, depending on what you are analyzing at the moment and how much risk you are taking. And they are closely related with how much soil characterization you have done, how sensitive you have worked on, the quality and quantity of your laboratory work and investigation work, and the consequences of failures, whether global or local, directly affect the choice of safety factor that we are using. So for basic civil work, it's not about a world of 1.3 for temporary and 1.5 for permanent stability factors. Speaking of mining applications, mine rock slopes are designed, luckily, with the aspect that probability of failure is associated. So the asset manager, the shareholder, wants to know how much risk he or she is taking if a consequence occurs. And we should also talk about the scale of the consequence if any failures and instabilities occur. Again, from the popular literature and well-established literature, besides of being popular, of course, a brief summary of what we have tried to describe: a range of acceptance levels of static safety factors for different structures compiled from the literature. So it all lies on what you're dealing with and how much risk you want to take. Glancing to Priest and Brown, 1983, for a threshold of safety factor of 1.0, they have tried to define the associated probability of failures of slopes, which means that if you have 100 scenarios for 10%, it means that 10 events will have safety factors less than 1.0. And the rest of the remaining will have safety factors greater than 1.0. So the minimum probability of failure corresponding to safety factor smaller than 1 corresponds to this explanation. Moving forward, it depends on your service life, your public liability, how many people will be affected by any possible consequence. Is there any monitoring program? What is your statistics and historical records of slope failures in that area at similar formations, units, and how well you have kept your history book and log for the former events. So that all together determines your thresholds for selecting the safety factor. Looking more detailed, again, into Reed and Stacy's book, it is clearly stated that, and it is widely applied in current practice. You have a bench width, you have a sliding wedge opportunity probability, which will require you to set up some sort of a backbreak distance and a usable width. So you want to avoid any rock falls, any wedge type instabilities, any planar instabilities, and overall instabilities. If you want to avoid an overall slope stability in your region, then you're in the world of 1.3 to 1.5 at least. And it will correspond to probability of failures being less than the risk taken for a bench stability study. To help you feel better, here's on the left side a bench scale failure, and in the middle there's an inter-ramp scale failure shown for illustrative purposes, and on the right side there's an overall pit failure shown, which hold different consequences, casualties, possible economical losses, and interruption of services at your organization. Back to the civil world. For those of you who are fairly familiar with designing with Eurocode, apart from the rest of the world, you are using a relatively slightly different approach by not just taking your best estimates of your strength parameters and dividing the resistive and the driving shear stresses with each other to find the stability factor, but you're applying your safety factors on the mechanical properties of the slope material, as well as surcharge loads and hydrogeological aspects where applicable, to come up with a satisfactory performance of 1.0 or other value in case it is defined. So what you're basically doing is you are applying the safety factors to the input parameters used for computing the shear strength. Some parts of the world in practice are also switching and progressing into the design criteria and practice, which is incorporating the basics defined in Eurocode 7. For I am sure that you're all familiar with the details, so I am not here to bore you or remind you about the code discussions, but just as a reminder to show you that at least, and as an example, slide 2, the 2D limit equilibrium slope stability software by Rocscience directly incorporates the coefficients, safety coefficients applied to the actions or the material properties or the resistances compatible with Eurocode 7. And of course, they are customizable. They have presets. We have preset settings, and you have customizable settings, which will directly apply the material factors, for instance, to the input parameters you define in slide 2, penalize them by the safety factors, and try to calculate the safety factors accordingly. So in order to save you time, you can just play with the coefficients of the design approaches in case you wish to achieve and come up with something custom and design your slope accordingly, assess your slope accordingly. Eurocode 7, design approach 1, combinations 1 and 2, design approaches 2 and 3 are already preset into the system. So we have talked about two slightly different definitions of safety factors. So moving on to how material parameter variability will affect your results, you can always conduct a sensitivity analysis. There's nothing complicated here. What you do is you select and you assign one or two strength parameters that you can include the unit weight as well, by the way, and the seismic forces and the groundwater levels, if I'm not mistaken, for a sensitivity analysis to just quickly have a feeling of what if scenarios. But be careful that while doing a sensitivity analysis in slide 2 or slide 3, it doesn't matter, it's all the same. Just one of the parameters is perturbated along your sensitivity range at a given time, while the other is being kept constant. Here's an example. Just don't mind what we have assigned for the parameters as an example. Here you see the change of safety factor within the slope section as a function of the internal friction angle of a more Coulomb material, and this is indicated in orange series, while independently conducting a sensitivity analysis on the cohesion intercept of the material will have less effect. Of course, it will change according to your choices, but if you're making a back analysis, it is a quick way of just back analyzing your system to have a feel of what the critical strength parameters can be for a failure case triggering. As we have indicated, you can conduct your sensitivity analysis to other parameters into the system, which will include the water table, the seismic load, and the tension crack depth, to get a feel of how those variables affect your safety factors without having to define multiple working files within slide. Now, moving on to probabilistic analysis, it is a whole different world than the sensitivity analysis. Using the probabilistic analysis option in slide 2, you can determine the effect of uncertainty and variability of input parameters on the results of the slope stability analysis. So the probability of failure can be estimated using a risk-based approach along with the deterministic factor of safety. So this gives you a feeling on how variability inherent in the nature or the way you collect data will impact your safety factors and give you a more powerful tool called the probability of failure to indicate, to model, to have a feeling of the risk that you're undertaking while conducting your slope assessment study. So this is essentially implemented to avoid a world that a safety factor of 1.01 is safe and 0.999 is unsafe. So we're not living in a black and white world in engineering, in all aspects of engineering, especially geotechnical engineering. And these are good numerical tools, provided that you use them accordingly with precautions. Now, the reason I have reclaimed the word precaution is that while randomly sampling our parameters, we should be careful about what we're doing. We'll take a look at it a few minutes later. In slide 2 and slide 3, there are essentially 3 different methods of random sampling. The most fundamental one is Monte Carlo simulation. The next one is Latin hypercube, and Rocscience has introduced a more rigorous and efficient way of sampling multivariate statistics parameters called response surface, which we will deal in a minute. Monte Carlo sampling is, as you know, is just the technique uses random numbers to sample from the input data probability distributions. Given that the number of samples you select are relatively high, Latin hypercube and Monte Carlo results are expected to converge into a certain level. But the penalty of Monte Carlo will be more execution time, computer runtime compared to Latin hypercube. So personally, I would say that we're not losing too much of sensitivity if we're sampling with Latin hypercube algorithm in a slope stability analysis with sufficient amount of samples. Another aspect that can be considered in a slope stability analysis that you run every day is the analysis type. You can conduct a run and reach a critical failure surface, a deterministic failure surface, and perturbate on the mechanical properties, strength properties of the associated materials to sample that set and come up with a probabilistic distribution of factors of safety, which will eventually lead you to statement of probability of failure, probability of safety factors being smaller than the threshold that you select. It does not necessarily have to be 1.0. You can set it to another decimal. By the way, if you do it with the global minimum setting, what you get is it will run and find the most critical slip surface for that problem, then use the probabilistic approach on that failure surface. So this saves you a considerable amount of runtime. If you choose the other option as the overall slope, then you have the opportunity to make a more rigorous analysis where you can use the random sample set to every candidate failure surface, regardless of their safety factors. So probabilistic analysis run over 10,000s or many thousands or hundreds of candidate critical surfaces to see if anything is missing from the global minimum assumption. Our suggestion at this point would be just to run a global minimum run get its results, and if really necessary, you can just put an overall slope analysis into an overnight run to see if there's a significant difference from your assumptions. Another aspect that we should be aware of is the possible correlation between the strength parameters. I am always giving the simplest example with the simplest failure criterion, material property you can find in slide 2, but however, you can use them in other material models as well. Cohesion intercept and angle of internal friction somehow should be correlated. And based on your laboratory data, and if you have sparse data to work on, and based on available literature, it is always wise to introduce some correlation coefficient for the randomization, so that in the probabilistic analysis, the system will generate a wiser set of random samples, which will prohibit you from getting failure probabilities or associated safety factors in the extremes. It doesn't matter, in the upper extreme or the lower extreme. What is essentially is the system at its most extreme point, to give you a rather meaningless but a remarkable example, it will not choose something like 1 degrees of internal friction angle and 0 degrees of cohesion, which will bring you to nothing and physically unrational. Then, after you perform your simplest form of randomization between cohesion and internal friction angle, of course, the result will differ for every slope stability analysis method you prefer. In this case, it's the generalized limit equilibrium. You have a histogram, a probability density function, and a best fit to it, which will reflect the probability of occurrences and associated factor of safeties. Here we have highlighted some columns which yield factors of safety smaller than 1, which we believe that they reflect actual failed cases within this randomization. Now, you have something more to talk about while doing your analysis. Going back to the required number of sampling to get a stable and reasonable result between the Monte Carlo Latin hypercube simulations and within a selected algorithm itself. Here we can say that in this specific example, generating 1,000 samples is not essentially considered to be adequate for reaching a stable value. If you just increase it up to 5,000, you see that you have reached an asymptote and a stable factor of safety. What I would just, if I'm after saving some more time in my subsequent analysis, I would cut down my sampling to 3,000, 2,000, 3,500. It all depends, and it's self-explanatory. Nothing too complicated and nothing new. Here you have all the tools that you can play with, but this will be essentially the essence of this session of my presentation. But I'm not reluctant to pronounce it once more, just in the middle. The essence lies in how you characterize, how correctly you interpret the behavior, how successfully you collect data, how correctly you estimate the potential mode of failure, and the rest is matched, and those are just easy tools that you can implement your engineering insight to come up with a resolution of your problem. You can imagine that applying all these randomization within a 3D limit equilibrium environment would require significantly much more runtimes, which would be impractical. And this is why the response surface algorithm has been developed and implemented in slide 3, then in slide 2 successively. In the latest versions of those 2D and the 3D limited equilibrium software by Rocscience, the response surface is already integrated. What response surface does, that it intrinsically selects some amount of the candidate surfaces and applies the randomization to those surfaces to have a feeling of where the most critical region and the slope unstable geometry surface or the volume in 3D case is present. As in the case of overall stability in slide 2, it uses the concept of wisely sampling the candidate volumes for studying the stability in the case of probabilistic analysis, so that it will not require the number of simulations required as in the case of a Latin hypercube, but would yield similar results. Of course, this is a very good example shown here for illustrative purposes, where the probability of failures are almost similar when the two different algorithms are used, but one cannot promise the success of and full 100% of 100% compatibility while dealing with other problem. So our suggestion would be just to quickly run a Latin hypercube simulation, and if you're curious about just run a response surface analysis, then of course make a more rigorous approach and run a Latin hypercube analysis based on those results. That would take more amount of time, but will sample almost every combination that you may face with. Another good tool and a feature included in slide 3 is the application of multiple minima. Again, rising from the same necessity and projecting the necessity of from time to time the need for analyzing the overall slope, the probabilistic approach applied to every candidate surface in 2D. It will be impractical to implement directly the same algorithm in 3D. So that's why Rocscience has developed to wisely choose a limited number of candidate volumes in 3D, then apply the probabilistic approach to those candidate volumes to aggressively search for the most critical volume within a reasonable amount of time. So very basic analysis to summarize what we have come so far. Basic pit geometry, simplified. Just do not concentrate on the strength parameters. We have two formations defined here. 3 methods for analysis are chosen in our simple example. We have defined the ellipsoid as the surface type and the cuckoo search algorithm, surface altering optimization. They are all custom and neatly developed features of slide 3 and slide 2, and it's a discussion for another session maybe. Here we run our analysis, then come up with the most basic results in the deterministic world. For the Bishop, the generalized limit equilibrium, and Spencer, we have similar deterministic factors of safety. Then we go and move on to the probabilistic world, choose global minimum as our analysis type, Latin hypercube as our sampling method, define the standard deviations and expected values, the median values for the parameters we are after, and of course define their form of distribution. Once we randomize and run an analysis, now we have again slightly median different values for the median factors of safety, but furthermore now we have the probability of failure values, which are more or less common and in compatibility. For the most critical slip volume that the software has encountered, Bishop differentiates from the rest in terms of slightly in terms of where the most critical failure volume is expected to be. You have a variety of options to see individual results of your safety factors, distribution of your safety factors as a function of randomized input parameters for every geological unit found in the model. I'm just passing all these. These are just good visualization tools to help you that you're approaching the problem in a correct way, that you're doing a good implementation of sampling, and whether your results are actually physically reasonable. Again, back to the discussion of which number of samples is the most appropriate that will converge to a stable probability of failure. Here is the result. We have run a perturbation analysis with a different number of samples used for 3 different methods, evaluated their probability of failures with respect to Monte Carlo and Latin hypercube methods at, let's say, 5,000 samples. They're not too much different from each other and can be considered as applicable. I can see that we're a little bit running out of time, and you have other duties to fulfill during this beautiful winter day. So I will progress a little faster just to sum up. Last words for the probabilistic analysis. We'll move on to spatial variability and discuss about what other options we'll have. It is always a good approach to just pick a section from a 3D analysis, carry it to a 2D analysis, and see how your analyses are impacted in terms of the deterministic safety factor and in terms of the results of a probabilistic approach. In this specific example, the deterministic safety factor, or the mean safety factor from a collection of random safety factors distribution, has decreased about from 1.2 to 1.05. However, the associated probability of failure has increased very significantly. So very different 2 conclusions you can drive from the same example by approaching from a 3D point of view and a 2D analysis. That's another discussion. I am not here to just answer all of them and answer that which is the best one, or if I'm doing something incorrectly, but these are just minor exercises and discussion points just to see the impact of choosing a wide variety of input parameters on your consequences. Moving on to preference of a response surface method rather than a Latin hypercube, you can say that we have actually obtained the same amount of sensitivity and the same amount of engineering conclusion, similar factors of safety, similar probability of failures, with exceptionally different runtimes. If you switch to response surface in slide 3D for randomization of a probabilistic approach in a pit, In a specific example, we have run this analysis in about 30 minutes, and if you just switch to a Latin hypercube, it will take you overnight, which will somehow bother you. So that's why response surfaces here. However, just glancing on the most critical volume in a 3D analysis does not necessarily mean that you should be looking at the same spot within your pit to see other alternatives which may be critical. So that sums up for the basic probabilistic approach and some pitfalls and some tips, humble tips from our side. I think it's a good point to briefly discuss the spatial parameter variability. Spatial variability can be defined as the location-based variation of material characteristics such as strength and unit weight in a material. Our first photo shows an instance where we have worked in a film characterizing a fill material in a dam embankment project, and you can visually see what has been going wrong, and the characteristics of the fill are even traceable from the surface, that they are slightly different. I can see that there are several questions. If I'm not able to answer them right now, I have them recorded and we will get back to you for sure. Just taking a second off, now we can just show you a second sample case where spatial parameter variability can be counted. This is from a slope stability problem along a dam access road section. The horizontal distance between the two boreholes are about 6 or 7 meters, essentially not much. And we were there to study the potential slope instabilities and comment about potential remedies at that section of the road. What we saw during our site characterization was that even though there was a little amount of distance between the two boreholes, this deformability characteristics within the rock mass differed significantly. So defining the correlation lengths in X and Y directions and accounting for spatial parameter variability in the assessment, slope stability assessment of such a problem is a good match to practically implement these issues. Besides some natural deposits, again in a dumped waste fill material characterization and at an open pit mining site, we have clearly seen and recorded evidences of spatial variability of dumped material, which differed in grain size and fines content, and we verified it with controlled pit loggings over the field, and we had a feel of how parameter variability was accounted for and could be accounted for to further study the slope stability of that dumped waste fill material in numerical sense. So the essence is, if you're not introducing any spatial variability, you have a constant strength value all over that body. If you are gently using a probabilistic approach, then that cohesion value, for instance, 37.5, 38 kPa, is randomized homogeneously all over the entire material region. If you wish to move on further and want to characterize the site as a random field of spatial variability for cohesion, then you will generate a random value for every material mass in every simulation, which will couple with the probabilistic analysis that we have explained a minute earlier, and account for the variability of soil or rock parameters throughout the body. Here we begin with an example, very simple example. Homogeneous slope, run a probabilistic analysis, less number of samples, Latin hypercube, nothing too interested, nothing too complicated. We intentionally wanted to keep it as a circular slip. You may comment on this, that this may not be the most appropriate selection, but we're not after this in the specific examples. Okay, glancing at the highlighted region, the mean factor of safety is about 1.39 with a probability of failure of 32.4. Now, we introduce the concept of spatial variability in 2D and define our correlation lengths. The question comes up like, how can I select my correlation lengths in both X and Y directions on a plane? Well, the easy answer is please consult to a selection of correlation lengths in the literature. They're not too much, and you can see that they already include a significant amount of variability within themselves. And my best answer would be that to characterize the site that you're studying on for yourself and check it with the findings from the literature in similar soils. Well, you may have some sense of feel on how correlation lengths may change in different types of soil, natural deposits in literature, but it's not the only case that we're facing in engineering, in geotechnical engineering, where, as a moment ago, as we have mentioned, we are defining artificial fills as waste materials, or we are using imperfect backfills in like in the case of mechanically stabilized earth walls. So they are very good candidates for characterizing your spatial variability parameters and applying to study how much the stability factor or the probability of factor is affected by these variabilities. Several studies in the literature that you may come across with and investigate further to addressing the impact of spatial variability to factor of safety and probability of failure. Here again, we have a very simple example. Continuing from the simple probabilistic case that we have introduced a moment ago, we have applied the spatial variability correlations into the system and have observed a significant impact on the mean factor of safeties as the probability of failures. For every sample which is randomized, you will have a different safety factor and a different candidate critical slip surface. Their distributions will vary compared to the case that you have only applied probabilistic analysis without spatial variability, and for the cases where you are free to select, of course, based on some field evidence and solid evidence, different correlation lengths. Even though here in this case, you see that for 5 meters and 4 meters of correlation lengths in both X and Y directions, although the mean factors of safety are not changed significantly, the distribution is impacted very much in the sense that once you are after calculating the probability of failures compared to a threshold of factor of safety 1, you get very different results for different correlation lengths within the same problem. You can try other extremes as correlation in X and Y are extremely different. I doubt if they hold any physical significance, but just for showcasing the numerical results and the impact, we have just intentionally put them into our presentation. I would argue that they would hold some meaningful significance for a X 100 meters and Y 5 meters material or case. Okay, you can have three different within slide 2, three different options of covariance functions to randomize your field. They are Markovian, 1D separable, and Gaussian, and all are explicitly defined within the help section. Not a dramatic change if you're dealing with simple geometry between the methods. I apologize, I am skipping these parts because we're running out of time. You always have the option to define a linear function for your strength parameter increment and still randomize it within this approach and get the safety factors and probability of failures. So lots of tools to play with, as long as that you're aware of what you're doing. Comparison with a constant cohesion intercept and a linearly increasing cohesion intercept. Impact on the mean factor of safety and probability of failure. Spatial variability analysis, we've shown it for a simple homogeneous slope, but it will be more effective if you have the opportunity to apply it for your real world cases where you can just assign them material specific. It doesn't have to be the same correlation length and properties and same variability for each material. You can assign them differently and see how the impact is. For further reading on random limit equilibrium and random finite element methods, I do not wish to take the credits because these works and the concepts and the implementations were mainly taken from the references listed here. They're not the only references found in the literature, but just a quick practical compilation of where you can refer to if you want to read further about spatial variability implementation in numerical analysis. So this is about to conclude our presentation for today. Thank you honestly for all the contributors and the patience of all of you who have been patiently following. There are about over 150 attendees who were kept online in this busy day. For any questions regarding licenses, trial versions, or features of the programs, you may consult us. And what's to come next is on February 16th, we're proud to announce that we will hold another event, and the registrations, I suppose, are freshly opened or about to be opened today, with our dear colleagues Buor, Octavian, and Deat Frank from Romania and Hungary. And it will be another co-hosted event, which will be of very much interest, I suppose. We are going to talk about the evaluation of rock slope stability related risks and seismic performance assessments of slopes in two different sessions. So, dear presenters and organizers, Professor Jovicic and Zoran, I am unmuting you with your permission to say the last words to our participants. Thank you once again for your participation.
Thank you, Anil, for this nice presentation, and I would like also to thank all participants that persisted, and the numbers are quite high and impressive for this very interesting seminar. Thank you.
Thank you, Professor. Your presence means much to us, and we hope this will be the only beginning of further cooperation.
Thank you.
Thank you once again. I'm kindly closing the sessions and hope to see you in the near future.